What is p-value? I know we know about p-value a lot, especially in the uh, research field. Even students, undergraduate students who have taken a statistics course, they are familiar with the concept called p-value. But it is very misunderstood concept. If you think you know what p-value means, you can stop this video for a while and then think about that. What is p-value? Try to come up with an answer yourself. Um, so, what is p-value? What in the world is p-value? Why is so much backlash against p-value recently, or especially after 2016, when American Statistical Association warned against using or abusing p-value to all the researchers who publish their research using p-value in especially in the psychology and medical medical science. Let's get down to the nitty gritty of p-value. What is it? What does p-value mean? Right? I know p-value stands for probability value. It is just a probability value. As you know, probability ranges from 0 to 1. 0 being the event is not happening for sure. 1 being event is happening for sure, absolutely happening. And we in research we use the standard cutoff to accept or reject our significance. Our study using the arbitrary number 0.05, which you also call significance level alpha. But what do you want? Why do you want our p-values less than 0.05, not higher than 0.05, right? Because remember, p-value ranges from 0 to 1, 1 being absolutely happening. Then we should be using higher p-values, right? Not lower. Higher p-value means the better likelihood of your data being correct. That feels right. But that's wrong. And that's not what p-value means when it was originally created by Ronald Fisher. So when he created the p-value for significance testing, he gave this definition, right? The definition is the probability of obtaining the test results, or whatever the test and whatever the data you get out of the research, data as extreme as, okay, this is very important, data as extreme as or more extreme if null hypothesis is true. Saying, assuming null hypothesis true, what is the likelihood of getting data as extreme as or more extreme, right? I know this sounds very gobbledygook, and yes, it does, in fact, unless we understand what that means, right? So p-value, this is the formula for p-value, right? Or this is just the schematic formula. P-value equals data as extreme or more extreme given, this vertical bar says, given null hypothesis is true. Okay, given null hypothesis true. What does that mean? You must have noticed that, right? It is a conditional probability. Whenever you say given and use the vertical bar, null hypothesis is true, that means you already assumed null hypothesis is true and then trying to find whether the data you got fits, right? So p-value is simply saying how surprised or you with your data if null hypothesis was true. And as you know, null hypothesis means there is no effect of a new drug, or the new drug is not different from the old drug. It is simply saying the status quo is correct, right? If you're testing your data against the assumption that null hypothesis is true, right, then higher p-value kind of helps your null hypothesis, your assumption, right? If you're assuming null hypothesis is true, then higher p-value means higher likelihood of null hypothesis being true. So let's say you got p-value of 0.10, right? What does that mean? Does that mean null hypothesis is 10% true? Is it 10% wrong? Or something else? Well, the p-value of 0.10 means there is a 10% probability, 10% chance of obtaining the data as extreme as or more extreme if null hypothesis is in fact true. In other words, you would get the data as extreme or more extreme than 10% if you repeated the experiments multiple times. Out of 100 times, you will get the data as extreme as or more extreme 10% of the time. That's exactly what p-value means. All right. So many researchers in their published articles misuse this value. They used it as a effect size. All right. Sometimes they used it as a null hypothesis being true or wrong. That's not what p-value means, right? They try to equate these two concepts, which is totally wrong. So p-value is very closely related to the prosecutor fallacy according to Bayes' theorem, right? What is Bayes' theorem? Let me see this. Let's say Bayes' theorem is asking what is the probability of null hypothesis being true given the data you got, right? And the formula for null hypothesis, Bayes' theorem is this: prior probability of null hypothesis being true is prior, so credence of your hypothesis, null hypothesis. What is the likelihood of getting data if your null hypothesis, assuming your null hypothesis is true, divided by total likelihood of getting data under both hypotheses, null hypothesis and alternative hypothesis, right? Probability of alternative hypothesis times probability of or likelihood of getting data under alternate hypothesis. And in fact, this value on the numerator, which says what is the likelihood of getting data given null hypothesis true, this is very closely related to p-value. However, researchers try to equate this with this. They try to come up with the answer. Hey, what is the probability of null hypothesis being true given the data? Which they didn't calculate this one. They calculated this one. What is the probability of getting data as extreme or more extreme than this given null hypothesis true? So these two values are not equal. They're completely different. So researchers misuse p-value and interpret some use as a effect size, which tells that what is the magnitude of the difference between treatment groups versus control group. And these are the points that American Statistical Association used to warn the researchers about using or misusing p-values, right? Number one being p-value simply says how incompatible the data are with your specified statistical model. It does not measure the, it doesn't tell whether the null hypothesis is true or not, right? Scientific conclusions or business decisions shouldn't be made just simply based on the p-value. P-value just gives you the directionality, right? Whether there is some statistical significance or not. It doesn't tell you how big is the effect size, right? And you have to report not only the p-value, you have to report a whole host of data, including what is the effect size, what is the false discovery rate, or maybe Bayes factor, which says what is the likelihood of alternate hypothesis being true compared to null hypothesis being true, right? This is simply the ratio of alternate hypothesis, odds of alternate hypothesis over null hypothesis. And p-value is simply a statistical significance. It is not a practical significance. Just because you have p-value of 0.0001 means you have a high, big effect size. There is no correlation. So you shouldn't use p-value as a silver bullet. It's just a statistical significance. It's not practical significance. That's what American Statistical Association warned researchers against. Now, let me illustrate. We talk about abstract about p-values a lot. Now let's get to the crux of what p-value means. Let me illustrate with p-value, right? With a coin toss experiment. Let's say you tossed a coin 10 times, and the coin landed on head 9 times. Now you need to calculate the probability and decide whether your coin is rigged or biased. Is it fair coin or rigged? That's you're trying to find out with the p-value. So there are two hypotheses, as usual. Null hypothesis says coin is fair, probability landing on head equals probability landing on tail, which is half or 50%. Alternate hypothesis says, hey, coin is biased toward head. Probability of landing on head is 0.7, or 70% time it lands on the head, and 30% time it lands on the tails. So that is your alternate hypothesis, and let's calculate p-value. Here, what is the probability under null hypothesis of getting 9 heads or more? Remember, p-value is data as extreme as or more extreme given null hypothesis is true. So it is asking what is the probability of getting 9 hairs or more hairs. That means 10 hairs out of 10 total toss. Now we need to use binomial expansion. This the formula n factorial divided by number of success, which is we can call landing on head number of success. K is number of success, and n minus k is number of failure. This gives you the binomial coefficient. And what is the probability of landing on head under null hypothesis, which is half? What is the probability of landing on tail under null hypothesis? Also half, 50%. So we simply plug in these numbers here. Probability of getting 9 heads is 10 over 1024. Now our calculations are done. We need to calculate 9 heads or more. So that means we need to calculate what is the probability of landing 10 heads out of 10 toss, which is very rare, but there is still number here. So whenever you say or in probability theory, it means plus. Okay, 9 heads or more means 9 heads. What is the probability of 9 heads? 10 over 1024. What is the probability of 10 heads out of 10 heads? Is 1 over 1024. Total probability is 0.0107, which is 1%. Now this p-value we got is less than 0.05, which is alpha, right? Our cutoff value for significant testing. Now, assuming null hypothesis is true, what is the likelihood of getting 9 heads or more? Is only 1%. Very unlikely, right? If null hypothesis is true, getting 9 heads or more heads out of 10 toss is very unlikely, which is just 1%. That's why we reject null hypothesis. Now, for the sake of argument, let's calculate our p-value. In this case, it becomes power under alternative hypothesis. In this case, we are calculating power, right? What is the probability of getting 9 heads or more heads out of 10 total coin toss, provided that our alternate hypothesis says probability of getting heads is 0.7. We are assuming our coin is rigged. That means rigged to our head. It lands on head 7% time and it lands on tail 30% of time. Now we simply plug in that value in the binomial expansion formula, which is k n minus k factorial times p k q n minus k. So 10 total, number of head is 9, number of tail is 1, probability of getting head is 0.7. this time it's not half anymore, this is 0.7, number of tail is 0.3, number of heads we got is 9, number of tail is 1. So for total probably getting 9 heads out of 10, total coin toss is 0.12. Remember, it is as extreme as or more. So we also need to calculate what is the probability of getting 10 heads out of 10 heads, assuming our alternate hypothesis is true, which is 0.0282. We need to add these probabilities, which gives you 15%. What does that mean? So if the coin is truly biased at p equals 0.7 toward head, then there is 15% chance that we see the results we saw, which is 9 or more heads in 10 tosses. Okay, we have higher probability of alternate hypothesis being true, which is 15%. Right, the likelihood of getting 9 heads or more, assuming alternate hypothesis true, is 15%. So it has higher likelihood of being true than null hypothesis. That's why we reject null hypothesis. That means power is, what is the probability of rejecting null hypothesis? True positive, right? Given null hypothesis false or alternate hypothesis true. That's the power, and we have 15%. And